Now, there are three factors that influence the rate of reaction. First is the concentration. Okay, concentration of reaction. Okay, if the reaction concentration is high, rate of chemical reaction would be, yes, low concentration. It will increase the concentration, and we can have uh, high concentration product, right? But there is a exception in case of gases where pressure is used in the case of gases. Okay, where in case of where we are using reactants in gaseous form, their concentration is directly proportional to the pressure applied. All right, right. And then what factor influence the rate of chemical reaction? Rate is what? Speed. Okay. The temperature. What kind of temperature is required? Appropriate temperature is required for a chemical reaction to take place. Okay. And then the third, very important, that is catalyst. Now, what is catalyst? Catalyst is a substance. Okay. Catalyst is a substance that does not take part in chemical reaction, okay, but increase or decrease the rate of chemical reaction. Okay, what is catalyst? It does not take part in chemical reaction, okay, but increases the rate of chemical reaction. We also use negative catalyst. Okay, what this do, it can be used to decrease the rate of, okay, chemical reaction. Okay, so catalyst can be used for both increasing or decreasing the speed of chemical reaction, right? Right. Now let us study what is rate law. Okay, now dependence on a rate of chemical reaction. Okay, dependence on rate of concentration of one or more reactants or products. This is represented by the rate law. If you can read here, rate law is a mathematical expression that that relates the rate of chemical reaction to molar concentration of reactants. The power of molar concentration may or may not be the same as the stoichiometric coefficient. Now, how we determine this? Okay, the power that we used for molar concentration, they may be same, they may not be same. Okay, and that is why it has been said that rate law, it should be calculated experimentally. Why it needs to be calculated experimentally? Because sometimes the molar concentration, their powers may vary. Okay, they may or may not be the same. And what does rate law do? It tells that the rate of concentration of one or more reactants, it is represented by a rate law only. Okay, right. If you see here, dependence of rate of concentration, rate law is the representation of rate of reaction, and it is expressed in concentration of reactants. It is also known as rate law, rate equation, okay, or rate constant. Okay, all right. For example, say, to understand rate law better, so these are some reactants and they are forming this product. Okay, this is a chemical reaction. Now, what will the rate expression for this? Rate expression, rate equation, rate constant. We can also call rate law, rate expression. Okay, so four names: rate law, rate expression, rate equation, rate constant. Now, what will be the rate expression for this specific reaction? Now, rate expression, it will be directly proportional to the concentration of the reactants raised to the power their stoichiometric coefficients. Okay, like this. All right, let us understood this rate law better. That what is the rate expression and rate concentration. Now here I have taken one example which I was writing, that see, this is a general chemical reaction, okay, where A, B, C, D, these are the coefficients of stoichiometry, or say stoichiometric coefficients of the reactants and products. Okay, now how we define rate law? As I have told you, rate law, it is directly proportional to the concentration of the reactants raised to the power their molar concentration, or raised to the power their stoichiometric coefficients. All right, if we replace this, or if we remove this proportionality sign, we obtain here proportionality constant, that is K. Okay, this K is called proportionality constant or a rate constant. All right, right. Now this is also known as differential rate equation. Why it is known as differential rate equation? Because it's in differential form. All right, d by dt. All right, where we have used this xy as the stoichiometric coefficients. Okay, these are the molar concentration of the reactants raised to the power. Okay, right. Let us do one example where we will calculate the rate expression. How we are going to write the rate expression? Now there is one condition that we were discussing, that rate constant or rate expression, that they may or may not be same as stoichiometric coefficient. Okay, they may or may not same as stoichiometric coefficient. All right. Now what that mean is, if we look at this reaction, see this reaction CHCl3 with chlorine, it is the product forming is CCl3 plus HCl. Now if we are going to write the rate expression using this, okay, that is rate is equals to K, that is rate constant, the molar concentration of the reactants, that is CHCl3, all right, and Cl2. Okay, now what we have written here, 1 by 2. For this we need to check if the reaction is balanced or no. Okay, rate expression, the variation in the stoichiometric coefficient, it takes place due to this point, that a reaction, chemical reaction which we are taking, okay, to calculate their rate expression, we need to check first if the reaction is balanced or no. Then only there we can see a certain change in their stoichiometric coefficient. All right, now if you see here, chlorine there are 4, Here they are 5. If we put here 1 by 2, the 1 by 2 will be the stoichiometric coefficient of Cl, of the concentration of chlorine, right? So this is how the stoichiometric coefficient, they may or may not be same as given in the chemical reaction, or say as given in the reactant species. All right. Right. Let us move on to our next topic, that is order of a reaction. Okay. Right. Order of reaction. So many questions asked in the exam regarding order of reaction, how we calculate order of reaction. Now, rate law, as you can read here, rate of the order of a reaction, it is the sum of the concentration of reactants in rate law expression. Okay, like we have given one example, and we have to calculate the order of reaction of that order of reaction. How we are going to calculate order of reaction? First, we are going to make the rate law expression as we just discussed. Then we are going to add the concentration of the reactants. Okay, this raised to power concentration, or say stoichiometric coefficient of the reactions. Okay, for this reaction, R is equal to Ka raised to power x and molar concentration of B raised to power y. We are going to add only this value to get the order of reaction. Okay, let's do an example. Say one reaction rate is given. Let's take another example before solving this. It's 3 by 2. Okay, and B reaction coefficients, they are given as -1. How we are going to calculate order of reaction for them? By simply adding these two. Okay, by simply adding the concentration of the reactants. Okay, so that will be 3 by 2 minus 1, because it is having plus sign, having minus sign, then plus minus will be minus. It will be 3 minus 2 by 2, it will be 1 by 2. Okay, right? So the order of reaction will be what? Half, right? This is how we are going to calculate order of reaction, which is very easy. We just going to add or sum the concentration of the reactants as given in the rate law expression, right? So let us see one more example that is given here. Here rate is given, and the concentration are given on the reactant side. How we are going to find the order of reaction? By simply adding these values, right? 1 by 2 plus 3 by 2, by LCM, by taking LCM we'll get 4 by 2, by dividing we'll get 2, which is the order of reaction. All right, now order of reaction, it can be 0, 1, 2 and 3, and it can also be in fractions. Okay, for zero order reaction, they are independent of concentration of reactants. Okay, right. Now there are different types of reaction: zero order reaction, elementary reaction and complex reaction. All right, now elementary reactions, for example, balanced equations. Okay, they may be a sum of balanced equation. They you can take that there may be a sum of elementary reactions, right? And for complex reaction, these are the reactions which take multiple steps to complete. Elementary, they are completed in one step only. Okay, for one or more than one step, for more than one step, say 2, 3, 4, 5, they come in the category of complex reaction. Okay, example of some complex reactions, they are, say, the oxidation of ethene to CO2 and H2O. Okay, now what happened in this reaction is one intermediate form. Okay, there is a formation of intermediate before the formation of product. Okay, that intermediate is formed of alcohol, aldehydes, and acids. Okay, then what is the molecularity of a reaction? Now, molecularity of a reaction, it depends on the number of reacting species taking part in the chemical reaction. All right. Molecularity of reaction. Okay. It depends on number of reacting species. Okay. That take part in chemical reaction. All right. Now, the molecularity of a reaction, how many types of reaction are there on the basis of this? There are unimolecular reactions, bimolecular reaction, okay, trimolecular reactions, depending on the molecules or say the reacting species, okay, present in the chemical reaction. Okay, right. So let us read the content. That the molecularity reaction is for complex reactions where the these kind of reaction, they involve more than 3 molecules. Okay, the reactions, they are completed in multiple steps. The complex reaction, they are completed in multiple steps. Okay, overall rate of chemical reaction, that is calculated by the slowest step, that is called rate determining step. Now, what is this rate determining step? It is also known as RDS. What is this rate determining step? Rate determining step. It is written here, first of all, it is a slowest step. Calculate the order for this reaction. Now, this complex reaction where we are having molecules, okay, this is a complex reaction. We are having more than 3 molecules, right? If I ask you to calculate the order for this reaction, the order, it appears to be 10, right? If you just look at the reaction, the order for this reaction, it appears to be 10. But this complex reaction is of second order. How come this complex reaction is of second order? Because of the slowest step, or say the rate determining step, that is taking place in the second step, or say in the first step of this reaction. All right. Another example has been given here for hydrogen peroxide, where the hydrogen peroxide, it has been decomposed in alkaline medium, right, in the presence of a catalyst, right? The rate equation given for this reaction is this. This is what? Instantaneous rate reaction. Instantaneous chemical rate. All right. Now, what is happening in this reaction? in step 1, H2O2 plus I, they are forming H2O plus IO ion, this iodide ion. Okay. Now this step is slow, or we can say rate determining step. Okay. From this step only, at whatever step we are uh, observing slow or say rate determining step, that will tell the order of reaction. As this rate uh, determining step or slow step is taking place in first step of the chemical reaction only, so we determined from here that the order of reaction is first. Okay, that this is first order chemical reaction. Okay, that the order of for this chemical reaction is 1. Now if we look at the step 2 of the same chemical reaction, what is happening here? H2O2, again in the presence of this iodide ion, it forms water, okay, plus I negative plus O2. All right. So both the step, if you check what kind of reaction is this is two-step reaction. This reaction is bimolecular. Okay. Both the step, both steps of this reaction are bimolecular. Okay. And this is a type of elementary reaction. Okay. That's one-step reaction. Elementary, where in the first step we are having observing slow step, that is rate determining step, right? So this is an example of elementary reaction also, right? Where intermediate is where here. This is intermediate, which is the slowest step of the rate determining, which is the slowest step of this chemical reaction that determines the rate of this chemical reaction. All right. So what we conclude from here is order. Order is what? It is an experimental quantity. Okay. We cannot tell just by looking at the reaction as it appears to be that it is having order like 10. Okay. We have to calculate the order experimentally. Okay. And what else? That molecularity of a chemical reaction, it can never be 0. Okay. Why? Because the number of molecules in a chemical reaction, are always whole entity. Okay. Okay. I hope you have understood the molecularity concept pretty well. Now the rate or the different step for these reactions, they have discussed here that it's a two-step reaction, and the first step, this is rate determining, where this iodide ion, this is acting as an intermediate. All right, and the above reaction is first order, as the slow step or the intermediate, it is forming at first step. All right. Right. So from this we concluded that order, it can be experimented, it can be calculated. Okay. It is an experimental quantity. Now let us do one question here, where the question is determine the order of reaction for a chemical reaction. Here say A and B, they are forming some product. Okay. Where rate of the chemical reaction is this. How we are going to find the order? Now this is simple. Just add the coefficient of the reactions. Okay. Here we will get 5 by 2 and the rate order of reaction will be 2.5. Understood? Right. Let us quickly see the difference between order and molecularity. Okay. The order It can have integral, zero, as well as fractional values, whereas molecularity, it can never be zero. All right, it can have only integral, or say whole number values, right? And order, it can be determined both for elementary and complex reaction as well. And molecularity, it can be determined for elementary reactions only, right? And in complex reaction, order is determined with the slowest from its slowest step. Okay, complex reactions are what? Reactions which are having more than one step. Okay, all right. And in complex reaction, molecularity, it is determined in each and every step. Okay, in each and every step, there is a change in number of molecules as a reaction is taking place. All right.